Welcome to the IpX True North podcast, where we connect people, processes, and tools. This is part one of two between Arnaud Hubaux, Senior Program Manager at ASML, and Maxime Gravel, Director of Model-Based Enterprise for IpX. In this episode, they're going to be talking about the challenges with maintaining the physics model within AI and ML.
Hi, my name is Arnaud Hubaux. I lead the development of performance applications for ASML lithography machines. Those applications combine physics and machine learnings, and they are used by our customers to detect defects during production or optimize corrections.
All right, hello everybody. My name is Maxime Gravel. I am the Director of Model-Based Enterprise at IpX. I'm very grateful. I want to thank Arnaud for sharing some of our time with us today. I got a lot of questions in my position working with people of all kinds of company to understand a little bit what is AI and how can CM support AI. So we're very grateful to have Arnaud today, and we'll try to better understand how can CM help with AI and machine learning. What really is going on? What are you doing at ASML today with AI, and what are the goals?
So we use it for two things mainly. First is deliver new products, so new value for our customers, and they are focusing on optimizing correction for the machines just to make sure they perform at their best. Also potentially identify defects during production. We also use it more internally to speed up manufacturing processes by qualifying parts, doing forensics analysis on parts to make sure that we only deliver highly performing parts as quickly as possible.
So Arnaud, just to understand well, you say you use AI both in your production to help optimize your production of your machine, and you also use AI or machine learning to help optimize the performance of your machine at the customer side.
Correct, yes.
And can you clarify high level? I don't know if all the listener here understand really what ASML does, but would you explain in a very short, succinctly a little bit, what are you producing? What is that ASML does?
So we simply make the machines that make the chips. So all the major chip manufacturers in the world are our customers, and we supply them with the equipment that turn their chip designs into physical chips.
And so if I understand well, ASML is not in the business of designing the chips themselves, right? This is not something, that's correct?
Yes.
And you're not always aware of how the supplier or your customer will use your machine to create design. You're typically not part of this process.
Correct, because that is very, very sensitive IP. So we provide the machines and they use those machines to produce the chips, but we don't know the chip designs.
That's very interesting. So you're using machine learning, right? What I hear is you're using AI machine learning to help optimize a process at the customer of manufacturing the chips, but you don't really know what the process is. So how does that work, Arnaud? How can you perform machine learning when you don't know exactly their design?
So the essence of machine learning is data. So it doesn't really matter when you get the data. What matters is that you get the right data for the job that you have to do. In our case, our systems are deployed in a customer environment. We don't have access to that environment. So it means that the machine learning solutions that we deploy have to be able to consume the data in the customer environment, use it to train themselves, and then perform. So that makes the design of our systems very interesting, because during development, we hardly have any data. So we have to work on all kinds of assumptions and experiments to make sure that once we have deployed the model in a very specific customer context, it will learn from that context and perform as the customers expect.
Thank you very much for clarifying that. So another question. So I expect there's a lot of challenges with AI, machine learning. Do you want to talk about a little bit of challenges you have today, and then we'll try to maybe try to relate if there's anything that could be supported by CM. So what are the main challenges you have, Arnaud, today?
The first challenge is explainability. because machine learning by design is figuring out correlations between your input data and the output. So what you want to predict, if it's a simple pass-fail or put a label on images. And because those models learn correlations, they don't necessarily provide you with an explanation of why, if you predict a failure, what is the cause of the failure. It will just tell you there is a relationship between these factors I've observed and the effects I see in the product. This is not what people want to do. When you are an engineer, when you are on the shop floor and you have to fix a machine, you are not looking for correlation. You want a causation. So this module is causing this effect on the product. So we need to make sure when we deploy machine learning solutions that in the system, we are able to provide a sensible causal explanation between the observed effects and what is really happening physically. So if you don't have this, you can't support the machines. So this is a short-term impact. And on the long term, you also cannot improve on your designs, because it's nice to say, okay, something is wrong, we need to fix it. It's very nice and short term, but if you can't find the root cause, you cannot improve on future design. So explainability is core. The second thing is that you want to guarantee performance when you install the system. So as I said, we don't know the data that the machine will see when you are at the customer sites. So during development, we have to make hypotheses on test data sets. So it could very well be that during your development, on the test data you have, your model performed fine. But when you deploy it, when you install it, performance all of a sudden starts to degrade because of data properties or other contextual events occurring. So we need to make sure that the pipeline itself is robust for those context-specific variations. That, of course, starts at install, but it continues then when the system is live and performing. Because like in any manufacturing process, drift occurs, and it is normal. So we need to make sure that the AI system, once deployed, can keep up with the drift and remain accurate. Another challenge, of course, is safety. So we need to secure that when machine learning is used to help and drive decision, it can never have any safety impact. So people's safety is critical. Also, you don't want to damage hardware. And finally, because when an AI is put in a position where it is making decisions, you want to make sure that it cannot have an impact on your overall production process. To give you an example, if you have a system that once a wafer has been produced, you want to determine if that wafer is likely going to be perfectly fine, or they might have issues. If there might be an issue, you want to reroute that silicon wafer to some special inspection tools. But if for some reason your system is predicting that all the wafers will be failed, all the wafers will be sent to this inspection queue, but then you will clog the whole manufacturing process. You cannot afford that. So you have to put some systems in place to prevent basically completely jamming the whole production process.
That's a very interesting challenge. Just for the audience here, you mentioned wafer, just to so everybody understand, when you say the wafer, can you explain what is the wafer exactly? What is
so
that?
Wafer is a silicon disk that is used to make chips. So on a wafer, you can have hundreds of chips. So you produce them on this big disk, and then you chop it into pieces, and every piece will be a chip.
And just for everybody to understand how critical a lot of parameters are for your process, if I'm not mistaken, you are manufacturing in the nanometer level now. We're looking at a
correct
strand of hair, and even smaller than that, correct? This is the kind of level we're looking at, correct?
Yes.
So I would expect that there's many causes or many reasons that could cause some drift of the process, I would expect, right? Temperature, environment, name them, anything that could impact the nanometer level, right?
Yes.
That is so this is quite a challenge. I one that really resonate with me, you mentioned there's also safety. I thought it was interesting. So obviously you want machine learning, right? You want some machine to take some decision, but it's something that we all not often forget, but safety is a very important thing. I would hope, I guess, how do you prevent that safety condition? Is there any Any specific things to do about that, or limit the capability of the machine to make decision, or how does that work?
Yeah, so to my knowledge, we are currently not yet applying AI where there could have impact on people's safety.
Okay, okay.
And we know there are parts of the machine that are they could potentially lead to very severe injuries, and these are guarded by very strict procedures for
Okay.
our engineers. And I don't think we'll ever let an AI drive that.
So at this point, you know for a fact that anything the AI or the machine learning, you're pretty much make sure off the bat that any areas that could impact safety are not today. You don't allow the machine to make these decisions.
No.
Excellent. So you brought a lot of good points with the challenge. It seems there's a lot of challenge in production at the customer side. You have many customer side, different environment. I assume the machine that you offer are very configurable also. I would expect that all machines are configured to the specific needs of the customer, I would expect. So one of the questions I'm asking from a CM perspective is we talk about baseline or try to understand that data. How do you control that baseline, or how are you able to control these parameters so the machine learning keeps doing what it's supposed to do? So can you elaborate a little bit on that baseline? Yes, thank you.
So I would say that we have two kinds of baselines. We have our design baseline. So this is where you, like for any hardware development, you want to determine exactly what is the bill of material, what is the bill of process, so what is the hardware that is part of the machine. Then we do the same for the software. What software is in the machine? What software configurations are allowed for a given hardware configuration? So that we can baseline up front. And then there is the machine in its, I would say, production baseline. And that is mostly determined by the customer, because as you said, we have thousands of parameters that the customers can tweak. They also have recipes they can use to influence the behavior of the machine. And those we don't know. So it means that when you do an update on the system, you have to make sure that after the maintenance operation, for instance, because you want to replace a part, the performance baseline of the system as it was before the part replacement and after, from a production perspective, is the same. And that baseline is maintained directly at the customer site. So for an AI system, it's even more challenging, because when you're swapping a part, you can be pretty predictable in the impact that part will have on the machine, and there may be some recalibration required. This is the normal process. When you talk about an AI system, it has learned from the data it has seen. Now, if you come with a software update, that changes, for instance, if you have a model that takes as input a number of physical models that are simulating heating behaviors, for instance. If you update that physical model, what will be the impact on the machine learning model accuracy is rather difficult to predict, because you don't know upfront what data it has seen. So it means that the qualification process for that new baseline must be it must be tightly coupled with the customer qualification process for that machine. So it's always going together with the customer. We do change the software baseline. We look at the machine performance baseline, and we make sure that after the update, the machine is still at the performance baseline that the customer requested.
Oh, wow. So, okay. So just to recap, I think what you say is there's two main baseline. One baseline is your machine, your hardware, your software, and there's thousands of combination thousands of configuration of your machine. This one, you say you have a better control. There's the other baseline that's at the customer baseline, the recipe and some maintenance they do. In this one, you don't have visibility. From what I get, it's a black box, right? It's
No.
more of a, you have, okay, it's not a black box at the supplier. You have that.
Well, well, when you really are at the customer side, I mean, you have to do your work, you have to troubleshoot, so you have access to some of the data, but you never have access to all the data. So you only have access to what the customer believes is required to perform the operations you have to perform. So, and sometimes those recipes don't even control themselves because they can change. So the customers sometimes have their own qualification process after our own qualification process.
I understand. So with these two baselines, so I would, okay, so based on that, it's two different customer may have different machine learning algorithm, from what I understand, based on what you say today also.
Because behind those, they actually, because for them, the machine is one of the pieces in the overall production process. So typically their manufacturing execution system is there governing the configuration and tweaking the machine. So that is in their system that we will never have access to. So this is why they run their own qualification process on top of ours to make sure that for their overall production process, the machine is performing the way it should.
I understand. Thank you. So with all these baseline, you know, in a CM perspective, we typically in change management or config management, when we do a change, we look at all the impacted, right? All the impacts to that. So we have a very good understanding of how we can do the impacts on your physical software, right? And your hardware. This is, well, pretty traditional configuration management. So now, how does this work when you do a change and you're trying to a machine? Let's say it's a change that it started from ASML and you're trying to understand the impact to all these algorithm or physics models. So how does that work, Arnaud? How do we do that?
So there is the, I would say, traditional part where you do your standard code reviews, for instance, for changing the model.
Yep.
You then run regular software and hardware simulations. You do failure mode simulations. So these are pretty traditional.
Yes.
Then what you do is based on data sets that are supposed to represent how the system is being used by some of our customers. You run the system through those predefined data sets, and you see if the machine learning behaves as expected. So if we change the let's say, physics model because we noticed there was an issue in it, and we fixed the issues, fixing that issue is supposed to improve the accuracy of your predictions because you remove, for instance, some noise in the models or incorrect parameters. By running those data sets internally, we can already see if the accuracy improvement we observe matches the expected improvement. So all these we can do in-house, and then we have to do again the same process at the customer side where we use their own data sets to qualify the upgrades. And sometimes we even have to do some canary testing where we run the old version of the system with the new version in a shadow mode. We let them perform together for a while. And only once we fully trust the newly delivered model, we will start using it in production. And another interesting aspect of those impact analysis is also related to export control. Because for traditional goods, it is very easy, not very easy, but for software and hardware, you know what it has been designed, you know where it is going, you know where it is used. Then for machine learning, it becomes a bit more blurry. And this is where it triggers very interesting discussions with legal departments. Because if you take a machine learning model, it's an algorithm. You know where it has been designed. But in itself, it is useless. You first need to train it for the model to start delivering valuable output. Now, the question is, if the model was designed in Europe, for instance, and you deploy it in the US, trained on data produced in the US, is it allowed or not? So this is just a case where you ship a completely untrained model. But now it becomes even more complex, where you have a machine that was manufactured in Europe, goes together with a machine learning model, goes to the US. It is trained in the US. It has learned on US data. Then you want maybe the US company sells this machine, and that machine goes to Asia. What about the training itself? Because the IP on the model is still within Europe, but the model has been trained with US data. So is it allowed or not? And if you do transfer it, can you even retrain that model to make it more specific for this Asian customer? So when you do impact analysis, you also have to look beyond just the technical aspects.
Okay, thank you, Arnaud. So pretty much what you say is if I recap what you said is in terms of impact analysis and understand there's if we wish some qualification, you when you do a change, you're always going to run that new change using a set of, if you wish, qualification data, right? Some pool of data that you're going to run internally and you're going to run with the supplier. That's one thing.
Correct.
So you got to keep that qualification data. That's a new baseline, right? We got to make sure you maintain that. And I would think, does that vary tremendously between different customer, or or there's a lot of baseline, or these? I understand the customer has its own set, but I would expect that this data keeps growing and growing and growing, or it's manageable in terms of qualification set.
There is a lot of variety in the data sets, because even for a single customer, as I said, our machines are made to make chips. And some customers, they produce the same chip for very long periods of time. So they are the data set. If you have one data set today, you know they will still produce the same chip in a year from now. So you can be pretty much okay by using a standard data set. Some other customers, they produce chip on demand. So they receive a design, they have to produce chips for like 3 weeks, and then they stop. So for those customers, it means the data set is first, it is a very short period of time, a very short lifetime. And when you want to qualify machine learning there, you also cannot afford to start from scratch, because by the time you have enough data, the product is already not manufactured anymore. So it means that you have to support those kind of use cases to apply techniques like transfer learning, where you look at products that were manufactured before, that had similar behavior, that you can take as input and then run it on the new products that will be coming. And you will still keep on training continuously on the new product design, but you don't start from scratch, because if you start from scratch, you will never have enough data to be able to reach the accuracy level the customer expects from the solution.
Thank you, Arnaud. So that qualification data also can evolve. I never had but as you do new product, you got to start with a set of data, so you don't have a fully untrained. I'm not sure if I'm using the right thing. A fully untrained machine learning or algorithm for the next production batch. Oh,
You
wow.
cannot afford that. And
No.
even on the single machine, the customers might process 10, 20, 40 different products with it. So every product has its own specificities. And it's not there is a one data set that will fit them all. It's not the case.
Very interesting. And the other thing that you just brought up is that concept. The other issue of impact is that export. Like you said, you're taking a machine with data that were gathered in a country, right? Or I would expect even from facility or a manufacturing facility to manufacturing facility. That's another part. Even the same data, what you say the machine learning may not exactly, you have to understand how the machine learning will predict the same data in a new environment, if I understand well. Wow,
Yes.
this is, okay, so this is another major challenge with AI and managing machine learning. Okay, thank you very much for this clarification. That's a good challenge. So the validation and verification, the qualification, I think we talked about it. That's a lot of it is involved with that. Is this part in the change process, as you do all, we don't want to slow down. I would expect also one other thing with machine learning, you don't want to slow down production or performance, right? You want to be as lean as possible in that change process. Once the change is done and you got to do that qualification, typically we're looking at weeks. Where is it a major part of the change process in terms of length, or typically this can be done fairly quickly?
No, it cannot be weeks, because as I said, if it's weeks, you're missing a new product that was just processed for 2 weeks. So it has to be in the matter of hours or days maximum.
Okay.
Already days will be deemed too much. So this is why you have to rely as much as possible on transfer learning, and also within a fleet of machines, because if you look at a production site, they don't have one machine, they have multiple machines. So
Yes.
to make sure that you learn as quickly as possible, you want to federate the learning from all the machines, put it together so that your model is again learning faster. And if you swap a part in one machine, the chances are that another machine already had seen this change before. So you don't again start from scratch with yet another type of change or recalibration that happened on the system.
This was very eye-opening for me. I did every time we talk with you, I learned more. And thank you very much for your time.
Thanks for tuning in. Make sure you subscribe so you don't miss part 2 coming out, where Max and Arnaud talk about data management for AI, warehouse big data, and CM.